So today we are talking about polynomial division, right? So before we left for break, which I understand feels like 100 years ago maybe, we looked at a bunch of factoring techniques for solving things where the degree is higher than 2, basically, because we lose the nice, handy, just do this every time formula stuff. The problem with, all the sort of cute little factoring tricks is that they don't always work, right? Factoring by grouping, common factors, treating a thing like it's quadratic and full or whatever. Those only work if, sort of things play out in the right way. So what we're going to look at today is kind of the, how do I factor the hard way? How do I factor by brute force when a thing doesn't factor otherwise? And the answer is division. Factoring is splitting a thing up into a product of multiple pieces. Division is the inverse operation to that. So we're basically figuring out, okay, if I know one of the factors, how do I find the rest of them by dividing? A little bit of terminology stuff first, just to make sure we're on the same page. So when I say words, we know what they mean. The thing that you divide, right, is the dividend. The thing that you divide by is the divisor. So if I'm dividing, I don't know, 16 divided by 3 or something. The dividend there is 16. The divisor is 3. The quotient is the whole number part of the answer, right? So how many times it goes in. So 16 divided by 3, 3 goes into 16. 5 whole times, that's the quotient. 3 times 5 is 15, so it leaves remainder 1. And really that remainder 1 means 1/3 left over, right? So 5 and 1/3 times would be 16 into 3. We're going to do this with polynomials. The way that we're going to do it is by adapting what we know about long division, and then we'll look at another method called synthetic division also, to work for polynomials as well. So just real quick, let's take a look at how long division works to kind of remind ourselves. If I want to divide 3 into, 40, what do we do? 3 goes into 4 one time, and then what? Put a 3 underneath because 1 times 3 is 3. And then subtract. So we multiply these, right? That's where that 3 came from. We subtract. 4 minus 3 is 1. 3 doesn't go into 1, but that's good because it shouldn't, because if it did, then we could have taken a bigger chunk in the first place, right? And then carry down the next thing. Or think of it as 0 minus, nothing. And then do that all again, right? 3 goes into 10 3 times. So I put a 3 as the next part of the quotient, the answer, right, if you want. And then multiply again. 3 times 3 is 9. Subtract again. 10 minus 9 is 1. And then we just, either add a decimal point and keep going, or say, okay, this is the remainder because this doesn't go into that, right? So how many times does 3 go into 40? 13 with remainder 1. So 40 divided by 3 is 13 and 1/3 left over, right? That's what we just figured out. The remainder was 1. The quotient was 13. Okay. Yeah. No. Yeah. Either one will be fine. We're going to look at both and then I'll say some more stuff about that. But yeah, no, either one is going to be fine. You won't need to do both. Okay. So what we're trying to figure out is how that works here. If I want to divide x squared plus 2x minus 3 by x plus 4. I'm going to set it up the same way. Now, doing division with numbers, the reason that we start with the first place is to sort of figure out how many times it would go into like the biggest chunk, right? And you kind of do that if you're doing like mental arithmetic too. Like if I say, hey, what's, I don't know, 350 divided by 3, you probably know right away 3 and 300, it's going to go 100 times and then some more, right? So you kind of do the same thing. You look at how much, how big can I chunk this up, and then I'll figure out the details later, right? We do the same thing here. What that looks like for polynomials is looking at how many times the leading term is going to divide into the leading term. So just look at those, forget anything else is even there for a moment. What's x squared divided by x? X. That's the first part of the quotient then. This thing goes into this thing at least x times, because x into x squared will go x times, right? Or this times this gives you that, if you want to say it that way. Okay. Okay. Then what? Then we multiply, right? We figure out, okay, well, what is this times that? I was able to kind of ignore the +4 part to determine like how many, sort of whole times it goes in. Now I have to actually look at it. So now we're going to take this and multiply by this. So what's x times x plus 4? X squared plus 4x. Okay. Then what? Subtract. Yeah. Just like with long division with numbers, now we subtract to figure out, okay, I've dealt with the leading part, right? I've dealt with kind of the biggest chunk. Notice when we subtract here, what's going to happen? That leading term is going to drop off, right? That's because I've dealt with the sort of biggest chunk of the thing already. Now we're working our way down and figuring out the details for, kind of the lower order terms. So those drop out. 2x minus 4x is negative 2x. And then negative 3 minus 0, because there's nothing in that place, right? Negative 3. Okay. Division, it's a division algorithm, just like with long division. So we're just going to do that again and keep doing that until it stops, until we get to an answer. So let's just walk through that one more time real quick. Leading term into the leading term, right? So I'm basically doing x squared divided by x, which leaves you the other factor of x, right? To get this. This times the divisor and subtract to figure out what's left. Now, once I get here, we're just going to do all that again. So I'm going to erase some of my notes here. We're going to do that again with those, right? So start over, forget about all this stuff, pretend like this is the thing under the little box, and look at how x goes into negative 2x. Negative 2 times, right? We want to match that term exactly. So negative 2x divided by x would be negative 2 times. And then we're going to do all the same stuff over, right? Take just that most recent part of the quotient, that last term I picked up, multiply by the divisor, bring all that down. So that would be negative 2x minus 8. And then subtract. This drops out again. That's good. That should happen, right? It should be reducing as we go along. And then negative 3 plus 8 would be 5. Yeah, be really careful with the signs. It's negative 3 minus negative 8. So negative 3 plus 8, so 5. That's the one thing I probably see most often in like grading long division stuff. there's a lot of arithmetic going on, and because you're subtracting at every step, there's a lot of, sign stuff to watch out for, right? So like, that's why I'm drawing these big sets of parentheses and stuff, just to hopefully help us kind of keep in mind that we are subtracting there. Okay, now, how do we know when we're done? Does this go into this? No. Not a whole number of times, right? It would be like a fraction thing, right? 5 over x. We stop when it becomes a fraction thing, just like we stop when it becomes a fraction in long division here, right? X doesn't go into 5, so we're done. This x minus 2 is the quotient. And 5 is the remainder. So what did we just figure out about x squared plus 2x minus 3 divided by x plus 4? I can break it up and write it as x minus 2 with remainder, or fraction part if you want, 5 over x plus 4. Okay, for the moment, mostly just the technique, like the actual method. So do we feel okay about how this went? Does anybody have any questions about any of the things that are happening here? Okay. Okay. That's great. Long division, just like long division for numbers, again, just basically gives us a way to sort of chunk the problem up and look at kind of one thing at a time, and also keep track of enough stuff that we're working the details out as we do it. Long division, you can divide any polynomial by any other polynomial. It's got to be kind of a like improper fraction thing for it to make sense. Like the degree on top needs to be bigger, or at least the same, for it to like go anywhere, for it to give you a quotient. When the thing we're dividing by happens to be linear, like it is here, another way that we can do this is a method called synthetic division that pretty much does all the same stuff, but we just kind of pare everything down as much as we can so that there's less to keep up with, and then just kind of organize it differently. So here's what synthetic division looks like. Again, this only works for a linear divisor, but for reasons that we're going to talk about in a minute, that's kind of all we really care about right now, in context of what we're going to do. So you are fine then to do long division or synthetic division. One or the other is going to be all you really need. If you go on and take calculus or something, you'll need to revisit polynomial division and brush up a little bit there. But for our purposes, synthetic is going to be just fine. So what we do for synthetic division is take the thing we're dividing, the dividend, right? X squared plus 2x minus 3. Now I know x squared minus 2x plus 3, I've got the quadratic, the linear, and the constant term. If I just keep those in order, just like we do for quadratic formula or whatever, then if I just keep track of the coefficients, that kind of gives me enough if I already know that they're in order, right? So I'm just going to take the coefficients, 1, I don't remember what they are now, 2, and -3. Again, that's just like the A, B, and C from the dividend. I'm going to leave a blank line under there and then just put this kind of frame thing in here. Okay. Right here, I'm going to put some information about the divisor, right? So some stuff about the divisor is going to go right here. We're dividing by x plus 4. So think about, and we'll look in a second at how this kind of ties into factoring and finding zeros and all that kind of stuff. if x plus 4 is the thing I'm dividing by, the 0, the value that would go with that would be -4. That's what goes right here. Okay. Now the way that the division algorithm works for synthetic division, instead of subtracting, we add down. So like within the columns, after each step, that makes it a little bit easier to keep up with some stuff because you're adding instead of subtracting. So we're less likely to make, sign mistakes and stuff. That means I start by taking 1 plus nothing. So 1. Right, so basically that first term just carries down. Then multiply. -4 times 1, -4. We go up and to the right and store that, right? So again, we're kind of working our way down. If you think about these as coefficients, right, on the square and the linear and constant, we're still working our way down the polynomial, right? We're just keeping track of things differently. But -4 times 1 is -4. That goes right here. And then we're going to add again. Just right here. 2 plus -4, -2. Now I multiply those, right? The -4 from the divisor with the new thing I just learned. -4 times -2 is 8. Since we just did this with long division, you see a lot of the same numbers showing up as well. 8 goes there. We add -3 plus 8 is 5. That's your remainder, right? Because at this point we're done. Like there's nothing else up here that I need to figure out or work through. So that last place is the remainder. These are the coefficients for the quotient. We started with a square thing and divided by a linear, right? So we started with degree 2. We divided out a degree 1 thing. That means the quotient is 1x minus 2 in the constant place. And then this is the remainder. Okay, my thoughts on this: long division is more stuff to write down. There are more places to make little arithmetic mistakes and stuff. And of course, if you make an arithmetic mistake here, it kind of throws the whole thing off because it all just sort of keeps going, right? That mistake gets passed on to the next thing and whatever. So there's that. But it's more familiar to something you already know. So hopefully it feels a little less like artificial, right? Synthetic division is a little bit, once you have the hang of it, it's a little bit faster and quicker and cleaner to write down. For what we're going to do, either is fine. You definitely don't need to worry about trying to do both. I would say if you're treating it like you're doing it from scratch, just do synthetic probably. If long division really, clicks with you and like you feel good about that, then do that. It doesn't matter to me which way you do it. I just need you to be able to divide stuff. Okay. That'll make sense. If you have any questions. Synthetic division is more, it's more like a trick though, a little bit, right? It's, do this thing, then do that thing, then do that thing. Hopefully this feels a little more like something that they could, seen before and makes a little more sense. But yeah, I'm good either way. Because really the thing that we care about is not like just doing the division stuff, but it's what we can do with it. We're still really interested in finding zeros of a polynomial, right? Solving polynomial equations. So there's this result called the remainder theorem that says that if you take a polynomial and divide it by a linear factor that looks like x minus k. Right? Now that thing is degree 1, right? It's linear, which is why synthetic works here. Then the remainder is equal to f of k. In other words, this problem we just did, if I took this function and plugged in -4, I would get 5, which is the same thing as the remainder. That's what the remainder theorem says. And you're probably thinking, man, that seems like a dumb way to evaluate a function. If I know what the function is already, like, why don't I just plug in? And you're right. That would be a dumb way to evaluate a function. Not dumb, but that's going the long way to evaluate a function if all I'm interested in is what's f of -4. But they're the same. And what that means is that in the special case, when that remainder is 0, if you divide something and you get remainder 0, what does that mean? It divides in, right? It's a factor, like 10 divided by 5, right? You get 2 with remainder 0 because 10 is divisible by 5. So in the special case, when that remainder is 0, that means you get a factor. And we've already seen in a bunch of places that if we know about factors, then we really know about zeros. And this special case of the remainder theorem called the factor theorem says that that works all the time. If you know about a 0, then you know about a factor. Or if you know about a factor, then you know about a 0. That's this if and only if statement. If I know a factor, then I know a 0. If I know a 0, then I know a factor, right? We've been using this all over the place, especially the graphing stuff. When you look at a graph, like you're going to do in about 15 minutes, and say, oh, 3 is a 0, 3 is an intercept. What does that tell you about a factor of the function? If there's an intercept at x equals 3, then there's a factor that looks like x minus 3. Yeah, x minus 3, right? Perfect, right? So if that's a factor, you set it equal to 0, you get 3 as the actual intercept, right? We've been using that to take a graph and figure out what its factors would look like. We've also used it the other way to look at a factored thing and figure out what its zeros are, right? Factor theorem says that always works. That's always true. That's how those things are related. So if I tell you, for example, that 2 is a 0 of this function, and I want you to find the other zeros, what I'm telling you is here's one of the zeros, but what that really means is here's one of the factors. If 2 is a 0, then the factor theorem says that what would be a factor? X minus 2 is a factor. If I take a thing that's cubic, that's degree 3, and I take out a linear factor, what's going to be left? 3 minus 1. So you're going to be left with a quadratic thing, and we know how to do those all the time, right? So what we're looking for are the zeros of this, or the solutions to this equation, right? That's what we're trying to do. Find the other zeros. We're trying to solve this. Why can't we use any of the other stuff we know about solving that? It's cubic, so I don't have a good, concise little like formula I can just plug everything into, right? Which means I got to go to my bag of factoring tricks that we talked about last week. Does this have any greatest common factors? No. Can I factor by grouping? No, because even if I pair these up, I'm not going to be able to, I can get something to take out of here, but 3x and 10, those don't have anything in common. So I'm not going to be able to make factoring by grouping work. And like, that's it really, right? Like that's the end of the list. So nothing we know gives us a way to solve that, except for this thing that we just found out about, that if I know a zero, then I know a factor. And if I know a factor, now that I know how to divide, I can break the thing down. So if 2 is a zero, that means x minus 2 is a factor. You want to do long division or synthetic? Okay. We might have time to just do both. X cubed minus 6x squared plus 3x plus 10. Okay. Hey, what do I know already about how this is going to go? Based on the information the problem gave us. 2 is a zero, right? So there's a linear factor. So when I do this division, what are we going to get as a remainder? 0. If 2 is a zero, then the remainder has to be 0, right? Because this is a factor. Being a factor means it divides in cleanly, means it leaves remainder 0. If I don't get remainder 0, I did something wrong somewhere, right? Like there's a mistake somewhere in there. Okay, so I'm just going to work through this. You know, work through it like along with, but x into x cubed. And multiply. And subtract. X cubed minus x cubed is 0. That's good. The leading term should be dropping off at each step. Negative 6x squared minus negative 2x squared. Again, this is, you know, probably the place where most, you know, errors and stuff happen, is just being careful with the signs. Negative 6 minus negative 2. So negative 6 plus 2. So negative 4. And then the other stuff just comes down. Anytime there's a missing place or a missing term somewhere, just treat it like there's a 0 there. So 3x minus 0, 10 minus 0. Okay, and then do it all again. Here. X into negative 4x squared. That's not what I want to be doing. Negative 4x. Okay, and then multiply. Negative 4x times x is, and negative 4x times negative 2. And then subtract. The term drops off. 3x minus 8x, negative 5x, 10 minus 0. So now we're looking here. X into negative 5x would be negative 5. And 5, or negative 5 times negative 2 would be plus 10. And that's good, because then when I subtract, we get 0. And now finally we get to turn a 0 into a happy face instead of a frowny face, because that's what we wanted to happen, right? The remainder being 0, that gives me a check on how all the rest of this went. I mean, we just did a bunch of stuff. You know, every step here, there's what, 2 multiplications, 2, like we just did 30 different arithmetic steps in there, any one of which I goof up a little thing and the rest of it's going to, you know, spiral on me, right? The rest of it's going to go off the rails. Getting 0 as the remainder there means that that all went correctly, right? Like there's almost no chance that you make a mistake here and then make a different mistake here that ends up, you know, sort of taking care of it. So that means I did everything right. What else does it tell us though? Like we're not done, right? We did the division. We got that the quotient is x squared minus 4x minus 5. What does that tell me about the thing I'm trying to do? We got one of the factors. One of the factors is x minus 2, because 2 is a 0, right? That's what the factor theorem means. What's the other factor? X squared minus 4x minus 5. And then we've got a product equal to 0. And what we've done is reduce this cubic thing that I didn't have a good method for solving to a quadratic that I do have lots of good methods for solving. X squared minus 4x minus 5 equals 0. I try to write these so that the quadratic, the quotient part should be manageable, right? That one factors, quadratic formula shouldn't be any big problem because the zeros are nice. It's x minus 5 and x plus 1. So I get 5 and negative 1. Now the question was find the other zeros. For stuff you're going to hand me, I just want to see that you got them all, right? For online stuff, it's probably going to be particular about the other zeros, right? These zeros are 2 and 5 and negative 1. 2 was given, so the other zeros would be 5 and negative 1, right? Yeah, so if it says other, those are the other ones. If it's all the zeros, then it's all of them. Just, you know, watch out for that. And if you miss it the first time, just make sure to read carefully and, you know, do that before you have it check the answer again. Because it might just be that. For stuff I'm going to grade, obviously I'm not going to be as particular about that. If you've done all this, you're good to go. Okay. So doing the division and getting 0 remainder, that gives me a check that I did the division correctly because I knew in the first place that 2 was a 0, right? That's why I'm happy about getting 0 remainder, because I knew that it was a 0, which means it must divide in evenly. Then I have to actually use that to split the thing up and solve and find the rest of the zeros, right? Okay. If in a hypothetical test situation, this were, say, the last problem on the test, so you're, you know, if you've saved it for last, you're maybe time crunched and stressed and whatever else. If you do all this and get remainder, I don't know, 3, what do you do? And hopefully you recognize that the remainder should have been 0, right? Because it was a 0. So I see that I get a remainder of 3, which means what? Something went wrong somewhere. Was it a big thing that went wrong? Was it not a big thing that went wrong? Check that you did this part right, of course, right? That you had the right divisor. But apart from that, it probably means that you goofed up some little arithmetic thing in here, which is going to be really hard to find. Like I have to grade a bunch of these, right? Finding your own arithmetic mistake is tough. Finding somebody else's is difficult too, but finding your own is even harder, right? Because you know, like, God, no, I wouldn't have done that, right? So you can either go digging and try to find the mistake and see if you can fix it, or you can scratch the whole thing and start over. Either one of those takes time though, right? Like you're going to do the thing over from scratch. That costs you 5 minutes or something. What else do we need to do in the problem? All of this. Okay. This is a 10-point problem or something. This is half of it. This is half of it. What you should not do is just bail and not do any of that, because that's going to cost you half the credit, right? So worst case, I don't have time to fix it. I made a mistake somewhere, you know, I got remainder 1. This would be a place where you could say, like, you know, just say, hey, Dr. Thomas, I goofed somewhere. I know this is not correct, right? Because I made a mistake, I can't find it, I don't have time to fix it, whatever. But here's what I should do now is take this and set it equal to 0 and continue solving, right? Like that's going to be a quadratic. You know how to solve a quadratic, even if it's not the right one because you made an arithmetic mistake. This is going to be a quadratic. I grade stuff following along with whatever you did, right? As much as I'm able and as long as it's, you know, like legible and whatever else, but following along with whatever you did. So you made a mistake here. I'm going to, you know, keep tracking and see if like, okay, well, did you do stuff right after that? So this, you know, I added those and I got 6 or something instead of 5. That's going to cost you like a point if you go ahead and do all the other stuff correctly. Losing a point on a problem is still an A, right? If you just see this and say, well, to heck with it, I'm done with this thing, and you know, don't do any of this stuff. Well, now we're talking about a failing grade, right? Because that's half the credit. So give me opportunities to give you partial credit, right? Show me that you understand big picture stuff that's going on, even if sometimes, you know, details get lost or whatever. Okay, that'll make sense. There'd be a few places like this where, you know, this is kind of the opposite of the, like, look at a graph and take all the information and just write stuff down, right? Everything there is right in front of you if you know where to look. Here, I have to do a bunch of kind of dense calculations and stuff to get there. And if I make a little, you know, simple mistake here, that like I make those too. Like if you make a little mistake here, everything that comes after it is going to be wrong because it all depended on that, right? So that's annoying, right? That's frustrating. That sucks. The thing spirals out of control on you. Sometimes you feel that as you're working through it, right? You're like, this can't possibly be right. There's no way he would have given me a thing where, you know, it's x squared plus 17 over 9, x plus 47 over 6 or something, right? So like you can feel that things are going wrong. But again, if you just bail because of that, that's going to hurt you more than if you try to sort of continue on, or at least explain, like, I know that I should now take this quotient, set it equal to 0 and continue solving, right? If it's real messy and you don't want to actually do it, okay, that's going to cost you a couple more points, but telling me that you knew what you should have done is going to, earn something still. Okay, that all makes sense? Okay. Let's do that one again real quick with synthetic, just for the sake of doing it. So again, I'm just going to take the coefficients, 1, -6, 3, and 10. I'm going to take our 0, which was 2. And then add down in the columns. So 1 plus 0 is 1. And then multiply. No, so 2 is a 0. So that's the other thing. When you do long division, you need a factor. So you take the x equals 2 and sort of move it over, right, to get x minus 2 equals 0. So long division, you take the factor. Synthetic, you take just the value, which I know is, opposite and weird. But again, don't try to do both. Just do one or the other. Right? 2 times 1 is 2. -6 and 2 is -4. 2 and -4 is -8. 3 and -8 is -5. 2 times -5 is -10. And then again, we get remainder 0. So this would be x squared minus 4x minus 5. Again, long division or synthetic, I don't really care. You're going to have to do it one time on the test. So as long as you can do that in under, I don't know, one about this same amount of complexity, as long as you can do that in, 2 or 3 minutes or something, you should be good to go, right? Okay. Okay, flip over and look at the back real quick, just to see kind of the kinds of questions I'm going to ask. And this is basically the questions that you would see in the homework. Use division and the remainder theorem to find f of 2. Well, of course, you can find f of 2 by just plugging 2 in. For the sake of practicing with division, though, you would divide by x minus 2 if you're doing long division, or you would put 2 in the little box if you're doing synthetic, and then find the remainder. Right? Whatever the remainder is, that's the same thing you would get if you just plug 2 into this. More to the point of why we care about this are the other questions. Use division to determine if 3 is a 0, if -1 is a 0. If I divide this by, again, 3 for synthetic or x minus 3 for long division, how do I answer the yes or no question about if that's a 0? Okay, if I just plug 3 in and get 0, then yes, it's a 0, right? And if I get something other than 0, then no, it's not. To use division to do it, it's all going to come down to the remainder, right? If I do synthetic and get remainder 1, then no. If I do synthetic and get remainder 0, then yes, it is, right? Or similar for long division. 6 and 7. Like example 2 that we just did, this is the kind of thing that I'm going to ask on a test question. I just won't even, be coy about it. This is the kind of thing I'm going to ask you about. If I give you a 0, go find the others, even when, you have to do it kind of the hard way, right? That's what division is letting us do. It's factor the brute force way. So if 3 is a 0, I divide this using 3 as my divisor, or x minus 3, and then find the other zeros by taking that quotient, the quadratic that you get, and solving it, right? So yeah, there are some problems to practice with. Again, stuff in the homework is going to look very similar to those things. So get on that. Once you've had a chance to practice some on your own, if we need to do another one tomorrow or something, we can. That's fine. For right now, though, we do have a quiz, so let's put things away.